friends, welcome back. We've been talking about different machine learning algorithms, right? And in the last video, we talked about the decision tree, right? So if I open this guy in here, we talked about the decision tree and we explained the math behind it and like we walked you through the theory of like how you can make your own tree. And we said that there is this factor called the Gini impurity factor that you use to decide what feature goes to the leaf node and the second node and the third node. Oh, sorry, the root node, the second node, and the third node, right? Um, Another feature that is also used instead of the Gini impurity metric is the entropy, right? I briefly mentioned it in the previous video, but in today's video, I actually want to talk about it and show you how you can calculate the entropy, right? Okay, so let's take a look at the data set that we had initially, right? This is our target. Let me change my, okay. So this is our target. I'm just going to call it T. And let's say that we want to calculate the entropy for this one. And I just call that feature 2. Or in this case, just like feature, right? So I go here and say for my target, right? I have 1, 2, 3 yeses. Okay, 3 yes. And then 4 no's, right? 4 no. Then you can calculate the entropy. Entropy of T would be the probability of positive. So minus, actually like this is in the equation, minus probability of positive or yes in this case. If you had more than 2 classes, then it's you repeat that for each class. Here we have yes and no classes, like only 2 classes. So I'm just going to go like positive and negative or yes and no. So probability is 3 over 7, because we have 7 samples. So 3 over 7 times log 2 of the probability, which is 3 over 7, minus 4 over 7, right, times log 2 of 4 over 7. You do the calculation and like you get something. So that's the entropy of the target class. And then you want to compare different features that you have, smoking, doing yoga, their age and stuff. And then based on the entropy that you calculate, you can decide what feature goes to the root node, right? In this example, let's do yoga. We called it F, and we go F equals. We have like, again, yes and no for each of them. So I'm just going to go for yes, right? So how many of it is yes? So this one is a yes, this one is a yes, this one is a yes, this one is a yes. So we have 4 of them, right? 3 of them are yeses. So I'm just going to go 3 yes, and then 1 of them is a no, and 1 no. Okay. And for feature no or negative, which is like not doing yoga, if you do a calculation, you'll see like this one is a no, this one is a no, this one is a no. So it's 0 yeses, right? And then 3 no's. And if you look at it, it adds up. So 3 yeses, 0 yeses, that's 3 that you see here. And then 1 no, 3 no's, that's like 4 no's that you see here. And then you calculate the entropy for this one as well. I'm just going to call that, for example, E1, and then you calculate the entropy for this guy as well, and that's E2. And then once you calculate those, right, you go the entropy or the information gain that you actually achieve from this feature in here. I'm just going to call that information gain. It's not the Instagram, it's information gain. That equals entropy of T, right, minus, right, the weighted average of these guys. So W1 E1 minus W2 E2, right? That's supposed to be a 2. So let's do the calculation. If I open my Python in here, and if I go Python 3, for example, so for example, we had 3 yeses and 1 no's. Just gonna go import NumPy as NP what am I doing? Okay, import numpy as np. And then I want to do the calculation, right? I want to go, for example, entropy. That's minus, we had 3 yeses, 1 no. So probability is 3 over 4. 3 over 4 times numpy, the log 2 of 3 over 4, right? Minus 1 over 4, because we only had 1 nose, times numpy, the log 2 of 1 over 4. And you gain 0.811, right? So for this one, E1, we'd actually calculated that, and we saw that it was 0.811. And then we can do this one as well, 0 and 3, right? So like if I do it here, you'll see it's like the probability is 0 times log 2 of 0 over 3. That actually is 0. Minus, and like there's a negative sign here as well. What's the probability of this guy? That's 1. And log 2 of 1, which is 0. So this guy is also 0. And then here you go E3 minus the weighted average of these guys. So we have 4 samples here. So if we want to do a calculation, we go ET, the guy that you calculate here, minus, this one has 4 samples. So 4 over 7, that times 811, right? Minus the other one has 3 samples, 3 over 7, times 0, right? You do this, and that's the information gain for this class. And then you repeat the same operation for this feature, and then this feature, and then the one that gives you the highest information gain, you actually want to use that for your root leaf, right? And then, like, again, you keep going down and you increase the depth of your tree, and you repeat these same equations for each step. Anyway, as you saw, like, really similar to the Gini impurity metric, but like also it's a different metric here. I just wanted to, discuss that before going to Python. But now that we have talked about it, let's actually open Python and start coding. The first thing we need to do is to actually see how we can implement it using the scikit-learn library, right? So I'm just gonna go from scikit-learn dot datasets, import, because I want to test it. So I'm just gonna bring load iris as well, and go from scikit-learn import tree, right? And then from scikit-learn dot model selection, we've seen this a lot, import train test split, and from scikit-learn dot metrics, import accuracy score, right? To see how well the model is performing. And to see the tree, I actually want to use the matplotlib. So from matplotlib, import pyplot as plot, and then finally import numpy. I need numpy because I want to set the seed. So I just want to go numpy dot random dot seed, set it to 0, for example, so that my result is reproducible. So I'm just gonna go iris equals, let's load our data set first. Load iris. Okay, good. And then we go x and y is iris dot data and iris dot target, right? So we have our x and y data. We had like this other option here to return x, y equals true as well. You can do it that way as well. Um, anyway, so let's go x train, x test, and y chain and y test. That equals train and test split, x, y, and then test size equals, I don't know, 0.4, for example. And now actually let's use the scikit-learn decision tree. So my classifier, CLF for classifier, that equals g dot decision tree classifier, right? And so as you can see, like if I do this again, there's this here, like we create our object, like a decision tree classifier object. You can provide some information in here as well, right? For example, it can go max depth is that maximum number of features, because like maybe you don't want to use all the features that you have, right? Maximum number of leaf nodes. You can play with all those arguments. I'll show you in a second. But now that we have the object, we can basically call one of the methods and go CLF, for example, equals CLF dot fit, which we train our model using the X train and Y train data. Now that it's chained, we can basically go Y pred equals CLF dot predict, and we pass in the X test values, and we can basically go accuracy equals accuracy score of Y pred, the values that we calculated, and Y test, right? And then we can go print, I don't know, with the classification accuracy is BCC times 100, for example. Okay, that's as simple as that. If I run this, what's happening? If I run this, oh, never mind. So it's being run, and it says the classification accuracy is like 95%. Okay, cool. It seems to be working, no problem. But let's say that you want to see the tree that you have. So scikit-learn gives you this cool option that you can go plot tree of the CLF, and don't forget to plot the show so that it keeps the photo, the image for you, so we can actually see. Now, if I run this, you will see the tree opens here. I can extend the size so that you can actually see better. It says that X2, which is the third feature, because like 0, 1, 2, less than 2.35, right? And that's the condition, and it gives you the Gini as well. It says, okay, the Gini impurity metric for this leaf node, for this root node is 0.663. There's like 90 samples in here, and you may ask, what is this value option? If you remember Iris dataset, we had 3 different targets, right? It could be class 0, class 1, and class 2. So these are the samples that fall into class 0. These are like 27 samples that fall into class 1, and 29 samples that actually fall into the second class, right? Or the third class, or class 2, if we go class 0, 1, 2. And then like you go here, you say, okay, the Gini impurity factor is 0 here, because as you can see, we have only like all the samples in this leaf fall into class 0. So if this is like one of the leaf nodes, we do not want to touch that again, because like it's like 100% accurate. And then like we go here, we make another decision, and so on and so forth. How many leaf nodes do we have? 1, 2, 3, 4, 5 leaf nodes, right? Okay, cool. We can play with this and say, as I said, for example, maximum leaf nodes, that's equal 3, right? If I run that now, you will see that the accuracy drops from 95 to 86%, right? And if I make this a bit bigger, you will see that, okay, this one is still like a pure leaf node, right? This one is impure, right? Like you have 27 samples that fall into class 1 and 2 samples that fall into class 2. And this is also like a pure. So if you would let it run more, like if I was not limiting the maximum leaf numbers, it would have like done some more optimization in this and like go like deeper one level and be like, okay, now I make it pure. So now I have 3. If you remember from the previous one, we had 5 because like we added the children of this node in here as well. Anyway, so this is like you can see the nodes and you can see the tree structure. You can play with like a smaller data set, right? And try to calculate the Gini purity metrics yourself to see like if you get it right or not. And as you can see by default, like I never specified this metric in here. Like I never told it to use Gini, but by default it's using Gini. If you don't want that, I think you could have changed that using this guy. That's, you see, like it gives you different options. If I go entropy and if I run that in here, it goes to like 95%. And as you can see, instead of the Gini, you can see the entropy metric in here, which is pretty cool. Anyway, that's about it. In the next video, we will actually start implementing our own decision tree classifier, this guy in here, and we'll see how we can implement that in Python. Thank you for watching me, and please don't forget to subscribe to my channel to support me, and also not to miss the next video when I upload it. And you guys take care. See you all in the next video. Bye bye.